Well, thank you for this opportunity to speak at this meeting, and I'm going to be talking about the SuperMuSR instrument. So let me just first of all remind you about what happens in a muon spin rotation experiment, because there are a lot of neutron experts here. So in a muon experiment, you implant the muon into your sample between two detectors, conventionally labeled forward and backward, and then the muon will precess in a magnetic field. Now, it will die at some point, and the rate at which it will die is governed by the muon decay rate and its lifetime, and you can see that in the green curve in the bottom left. It's just radioactive decay. But superimposed on top of that, if you look at these two different detectors, forward and backward, you can essentially measure the polarization of the muon as it rotates. And if you take those two signals and subtract them, you can measure a precession frequency. And this allows you to measure internal fields inside samples. Now, let's just have a look at a particular example. This is sodium iridate, which is a material that was very interesting because it was a KTF magnet candidate. It also turns out to show zigzag order, and very early in its history, we're able to show using muSR that it has long-range magnetic order. You can see these wiggles at 8.5 Kelvin, and this is indicating the order parameter of the magnet, and you can see its temperature dependence on the right. Now, actually, these data were taken at PSI, although we first took a data set at ISIS. And the ISIS data you can see on the right, and you can see that there's a problem with the ISIS data. It's essentially because the problem with the pulse source is you don't have high frequency resolution. And so those oscillations are wiped out. So the problem, if you like, with a pulse source is you have a blurred vision of the world. You don't have that fine time resolution. And this comes about due to the fact that the pulse that is producing the muons from the accelerator has a non-zero width. It's not a delta function. And also, there's also a contribution from pion decay, and this also contributes to the width of the pulse. And so continuous sources like PSI or Triumph have a great advantage over pulse sources. So why do we need pulse sources? Well, we lose on resolution because of those features, but we win on a number of other things. And in particular, we win on rate. So in a continuous source, the rate at which you can obtain data is set by the muon lifetime, because you have one muon in your experiment at any one time, you wait for it to decay, then you let the next one in. And if you try and let too many muons in, you just don't know which one has decayed. At a pulse source, your limit is really just set by the intensity of your accelerator and your number of detectors. You mustn't overwhelm your detector dead times. So if you put more detectors on, your rate goes up. And actually, since the time I've been doing muSR in my career, continuous sources have been flat in their rate. ISIS has just increased. You also win because you can apply pulsed excitation. So there's a whole set of experiments that are much better to do at a pulse source. And you win on low background and the ability to measure out to very, very low times. Very long time. So, and the reason for this is that essentially you're measuring for the order of 20 microseconds, but the pulses only arrive every 20 milliseconds. So for most of the time, you're not measuring. And any background is likely, therefore, more often than not, to hit your detectors when you're not measuring. Now, the key strategic question is, can you engineer your way out of the losses, the low resolution, and can you capitalize on your wins? And that's really the strategy that lies behind the SuperMuSR project. Now, I haven't got much time, and so I'm going to give you one science example that will motivate some of this. And I'm afraid it's not a material of the future, it's a material of the past. So I'm sorry about that. This is sodium fluoride. Very, very simple material. Sodium chloride structure forms a three-dimensional lattice. And the muon, we know, sits between two fluorines and between two sodiums in that position. Now, it was discovered very early in the history of muSR that rather than just seeing an effect due to nuclear dipoles that maybe gave you some Gaussian broadening, you saw these rather beautiful oscillations. And what's going on here is that you have something in your crystal which is analogous to the bifluoride ion. Your muon has gone between two fluorines, and you get this beautiful quantum oscillation that is occurring due to the time evolution of a wave function of the entangled state of the muon and the two fluorines. And the frequency of these oscillations allows you to work out the muon fluorine distance. So it's a beautiful effect. It's seen in a lot of cases. So this is some example of molecular magnets, much more complicated materials. These are materials of the future, but it turns out you can see the same kind of fluorine oscillations in these materials above their magnetic ordering temperatures. And this tells you things about the muon site. let's go back to something really simple again, calcium fluoride. I like this one because the calcium has no nuclear moment, so you only have to worry about the fluorines. And so if you take your muon here, it's between two fluorines, but actually what about the other fluorines? Now, if you start including your next nearest neighbor fluorines, you actually enlarge the size of your Hilbert space because each of these spins can be up or down. So in fact, you have a Hamiltonian, which is 2048 by 2048, but you can process that. Now, of course, there are a lot of other fluorines in the crystal, and you really want to include those as well. You can't do that exactly, but we have a method for including that as well. And the other thing I should point out is that the muon pulls the nearest neighbor fluorines in, and this is an effect that we've been able to study using DFT. So you can see this effect between the fluorines pulling the muon pulling the fluorines in. If you go back to sodium fluoride, you have something similar. The muon between two fluorines, it pulls them in, pushes the two sodiums out of the way. Here you have to include the sodium nuclear moment. And we've also included some other fluorines as well in our little cluster that we time evolve. And when you do this, the rather beautiful thing is you can fit these oscillations perfectly. So the dotted lines here are what happens if you ignore anything other than the two nearest fluorines. If you include all of the nearest neighbors, you get the solid line shown for calcium fluoride and sodium fluoride, and it works beautifully. So I'm not going to go into any more details of that, but just really to say that to do these measurements, you have to be able to measure out to long time. If you compare these data with the ones measured in the 1980s on a continuous source, you can see we have much better long time data here. Just to give you another example of this, if you take the compound potassium phosphorus fluoride, KPF6, then this shows you some simulations of the muon being in different places. And the thing I just want you to take away from this picture is that for these different muon sites, when you do the simulation, the oscillations look completely different. So you really have sensitivity to your muon site. It's very, very sensitive, the shape of these oscillations, just due to the coupling with all of the next nearest neighbors. And it turns out that the site that DFT predicts completely agrees with the data measured out to long times. And we can even do crystallography without doing crystallography. So this is lead fluoride. Our sample was alpha lead fluoride. We actually measured it a large number of years ago. But what we've been able to show now is if you do this analysis, you have different curves for alpha and beta phases because lead fluoride has these two different phases. And the interesting thing is if you just had the early time data, they look pretty similar, but you can see at late times they depart. And indeed, the one that agrees best with the data, the red curve, is the correct crystal form. Okay, so the point here is that to get this additional information, you need high statistics. Now, a typical muon data run, when I guess many of us started doing muSR, was a typical run would be 10 or 20 million events. These units are million events, not MeV, not a million electron volts. So 10 or 20 million electron volts, which is about 1 hour, at a continuous source, or indeed at ISIS in the 1990s. Now, because of the detector enhancements, we can typically run at 50 or 100 or even more million events per hour. But really the standard we want now for these data, the data we've been taking recently, have been 1 billion events. That's really our basic minimum. And that takes, of order of a day or half a day now. SuperMuSR would be able to achieve this in under an hour. So this would be the new gold standard, this kind of statistics. And of course, if you counted for longer, in a day, you could count 30 billion events. Now, this allows you to access these weak couplings that only show up at late times as standard. Whereas at the moment, it's really rather an exceptional thing. You have to blow all your beam time on counting out to very long times. So this isn't just more statistics because we want to just measure things more accurately because we're physicists and we like doing accurate measurements. This really shows up new stuff, and weak effects where there's a lot of important physics show up when you have high statistics. Okay, so where are we at the moment? So this, if you like, is a schematic, a dumbed down schematic of the current muSR experiment. The muon beam comes from the left, you go through slits, you go through a quad doublet, and then you hit the instrument. Now, this is what's planned. This is the SuperMuSR experiment. It's aimed to give 10 times better resolution at an enhanced rate, or an equivalent resolution to what's available at present, but with 15 or 20 times the rate. And this really will allow us to do new things. This really is a super SuperMuSR instrument. So we can leap over tall buildings just like Superman with this design. Now, I talked about one science example, which is one I'm particularly interested in, looking at the decoherence effects in fluoride networks and characterizing these sites. But there's a whole lot of new things that will lead to new results in terms of a whole range of different science areas. So this is a table, I haven't got time to go through it all, but basically showing you that in different areas, either this possibility of the high rate or the high resolution or some combination, or indeed the possibility to manipulate the spin direction. At the moment, the spin direction in a muon experiment at ICIS is limited to being along the beamline, or very, very slightly canted out by a degree or two. In the future with SuperMuSR, we will be able to rotate the spin around, as is done in a number of continuous facilities. So this will allow us to got unmuted. Okay, so this really is a key slide for understanding how the high resolution works. So what's shown here is a figure of merit. This is essentially telling you about, you can think of this as rate, but it's slightly different. It's essentially what you need to do a good experiment. And this shows you this figure of merit as a function of frequency. Now, if you look at a continuous muon source like PSI or Triumph, you're essentially on that line. So you have a very good frequency resolution. It's pretty uniform across the board. But the thing that you are stuck at is this maximum rate, which is set by the muon lifetime. So there's not a great deal you can do about that. Where we are with ICIS at the moment is in that black line at the bottom left-hand corner. So we don't have a great deal of frequency resolution, but we do have a better rate, and that rate is increasing. So it allows us to do slowly relaxing or slowly oscillating physics very, very well, but we're stuck there. Now, with the new instrument, what we would be able to do is operate in a high rate mode where essentially you already get a frequency boost just because you've got more muons. And so your rate would greatly increase. And this is the thing that I'm particularly excited about for these fluorine-related site determination measurements and looking at decoherence. But you'd be able to work in another regime as well, where you start slicing the pulses. So I'll say a little bit about that in a moment. But what that does, it cuts your rate. But what you can then do is have a narrower pulse because you've sliced it, and you can get an enhanced frequency resolution. And actually, if you can get up to a decent rate at sort of 40, 50, 60 megahertz, there's a lot of science that you can then do, looking at magnetism, superconductivity, a whole range of other things that are tricky at ICIS at the moment. And certainly that experiment I showed on sodium iridate right at the beginning of the talk would easily be possible at ICIS with the SuperMuSR instrument. Now, the other thing is we could actually work in what I like to call a blended mode. So you could imagine doing an experiment where you switch from one mode to the other. Now, in the neutron community, you're very used to taking detectors from different banks, which have different characteristics, and knitting that data together. We would have to invent that kind of thing if we were going to work in a blended mode. But I think that would give us a number of advantages. You get high rate for the early times, and you could knit that together with high resolution. Sorry, you get high resolution data, fast frequencies at the early times, and you'd use the high rate mode to get a really good imaging of the late time data, and you could then knit those together in a blended mode. This is how you do the pulse slicing. So essentially, this is showing the muon pulse slowed down. You can see the number of nanoseconds on the right slowly increasing. And by essentially applying a very fast electric field, you can switch the beam from going into your instrument to passing harmlessly away from it. And this technology has already been developed for the ICIS kickers that we use in the present configuration. This would be an enhanced version to allow doing this pulse slicing, but the technology is entirely feasible. We would need new detectors for the high rate, and this is the current design with 12, 16 elements. So this would give you, this allows you to cope with the high rate of the incoming data. And you would have a spin rotator also on the beamline that would allow you to extend measurements to high magnetic fields, measuring magnetism and superconductivity and permitting experiments in new geometries. So this is what the experiment would look like. This is the beamline. shown in a cutaway. You can see spin rotators, you can see the quad magnets and the pulse slicer in the middle. This is the three-dimensional representation. You can see the beam is being operated by the ex-members of Daft Punk, it looks like. I don't know why that's done. But the crucial team here that is behind all of this are the people at ICE, led by Peter Baker and his colleagues listed here, who are really doing so much work in the development and the ideas of this new instrument. And this just basically is my summary of what we could do with SuperMuSR. We would have enhanced rate, enhanced resolution, spin rotator capability, the possibility of this new blended mode. It would enhance the existing science, enable new science, and would really give ICIS a next generation instrument to take us through the next decades.
Steve,